last time, so what I'm going to do is I'm going to skip over this diver example. That's one of the things that's in the labs, in the worked examples. And we're going to skip on to variable acceleration, right? So I'm expecting that you all know about constant acceleration under gravity, so free fall, and we'll skip over that and the diver example, but that's on the website. You can download it, and it'll explain how to solve that in detail there. So what we're going to skip on to is variable acceleration, and when we're dealing with variable acceleration, we cannot use our constant acceleration equations because we've got a continuously varying acceleration. Neither can we split the problem up nicely into different sections where we have a constant acceleration in each section, because we can have an acceleration that continuously varies. So for example, a rocket that's launched from the ground typically has a constant thrust. So that's a constant force pushing it forwards, but as it's burning fuel, its mass is changing, and as we'll see when we do Newton's laws, that leads to an increasing acceleration. So the acceleration of a rocket typically continuously increases, and so you end up having to use calculus to solve the problem. You can't use constant acceleration equations. And so when we went through the discussion of acceleration and velocity, we developed these differential formulas. So velocity is the differential of the position with respect to time, and the acceleration is the differential of the velocity with respect to time, that we can also write here as a second order differential. So that means differentiating the position with respect to time twice. And then we also looked at the area under those velocity time plots. And if we looked at the area under a velocity time plot, we could integrate to calculate the area, and we showed that that was equal to the change in position, or the displacement. And similarly, we have an integral relation for the change in the velocity, which is the integration of the acceleration with respect to time. Right? So if you plotted an acceleration versus time plot, the area under that plot would give you the change in the velocity. Right? So these are the relationships that we've already seen. And so this is similar to the example we did last time in the lectures when we were discussing this. If you're given the velocity as a function of time like this, we can ask ourselves, what's the acceleration and what's the displacement? Right? So if we're calculating the acceleration, we use this relationship here. The acceleration is the differential of the velocity with respect to time, and then we just differentiate this expression here with respect to time. So we reduce the power of t by we multiply through by the power of t, so that gives us 6, and reduce the power of t by 1, so that gives us t. And then we do the same here. This is t to the 1, so we get 1 times 2 is 2, and then t to the power 0 is 1. And so we end up with this acceleration is 6t plus 2. So for the displacement, what we're going to do here is we're going to integrate from time t equals 0 to time t some point later. And for this, we're integrating this expression with respect to time. So we increase the power by 1 to give us t cubed and divide by the power. So that gives us just t cubed because the 3's cancel. And here we increase the power by 1, and that gives us t squared. We divide by the new power, and so that 2's cancel, and we end up with t squared. And then we evaluate that between t and 0. Well, when t is equal to 0, this expression is 0, so our constant is going to be 0, and then we just get t here. So we end up with our displacement is t cubed plus t squared. And there's a worked example in the kinematics examples about a marble that's actually more complicated than this, and at a level beyond what I'd expect you to be able to reproduce in the exam in the first year. But that gives you another sort of insight into how to use calculus to solve these problems. So generally speaking, this is probably as hard as it will get, maybe a little bit beyond this. But about this level is what I would expect you to be able to do in the exam if you're given some expression for the velocity or displacement or acceleration as a function of time. I'd expect you to be able to calculate the other two quantities by integration or differentiation. Okay, any questions on that? But it'll just be these polynomial formulae to keep the calculus simple. Okay, so up till now, we've been talking about motion in a straight line. And so we've only been talking about stuff that's been moving in one dimension. But obviously we live in a three-dimensional world, well in fact four-dimensional, but we'll get to that at the end of the course. So we've got to talk about motion in 2 or 3 dimensions. And so what we've got to do here is, remember we talked about all these things being vector quantities, and so when we have vectors, if we go to 2 and 3-dimensional vectors, then we have 2 or 3 components to the vector. So when we were doing one-dimensional motion, I kept drawing the little arrows over the top to denote they were vectors, but a one-dimensional vector is mathematically very hard to distinguish from a scalar because it's just got one component, it's a number, and it tells you, how far in that one direction that you're allowed to move you've gone, or how fast you're moving in that one direction. But once we go to 2 and 3D, we have 2 or 3 components, and these things do become recognizable as vectors. And so what we do when we're solving problems in 2 or 3D, what we have is that each component can be treated independently. So we can separate the components into x, y, and z if it's 3D, and then we can come up with equations for each component independently, and then the thing that links the components together is that time, right? Because the initial and final velocities, of course, in a particular direction don't matter, but the time is always the same for both x and for y. So usually we end up calculating time from one component and using it to solve what's going on in the other component, and we'll see how to do that in a minute. Oops. There we go. Not that exciting. So we've now got velocity and displacement, and we've got the same relationships that we had before between velocity and displacement. Velocity is the rate of change of position, rate of change of displacement. But now we have 2 dimensions, so we have a 2-component vector if we're doing it in 2D, or 3 components if we're doing it in 3D. And typically, I don't know why the convention is this, but typically when we're talking about multiple dimensions, you will often see the displacement vector written as r. Right? That's just a convention. You see it written all over the place as r. I have no idea where this came from, but it's very common when you're talking about multiple dimensions to refer to the displacement here vector as r. And we can split this into its x, y, and z components. And when we come to calculating the velocity, just as we had before, the velocity is the differential of the position with respect to time. So we can write it like this, where we have this vector here, but now this, of course, has got a 3 components, an x, y, and z component. So better switch that. There we go. So what we've got is we've got our position vector here, which is equal to, what did we say, x, I plus y, j plus z, k. And our velocity vector here is equal to the differential of r with respect to t. So it's the differential of this with respect to t. So if I write this out longhand, what I'm going to get is I differentiate the first component, so I get dx by dt in the I direction, plus dy by dt in the j direction, plus dz by dt in the k direction, where these are all vectors, unit vectors. So when you differentiate, when you're calculating the velocity, you can differentiate each component of the displacement independently, right? We differentiated each of these independently, and so you end up with each component in the x, y, and z direction is just the rate of change of the x displacement, rate of change of the y displacement, rate of change of the z displacement. So again, we're treating each of these three components independently, and we differentiate them each independently. And we can do this again with the acceleration. It's just the rate of change of the velocity. And so we can go through this exercise again and differentiate. So this is now dv by dt. And so if I differentiate the I component again, I'm going to get the second order differential in x, second order differential in y, and second order differential in z. Right, so again, I'm just repeating the exercise. Or you can express it here in terms of the components of the velocity, the velocity. So the x component, y component, and z component, each independently differentiated with respect to time. Okay, so now we've got 2 dimensions. We have a whole range of directions that are possible. We're no longer talking about, the acceleration pointing in the same, has to point along the same single axis that we have for all the other quantities. We've got a freedom to point it in any direction. So we now have to ask ourselves is, what is the relationship between the directions of the velocity and the acceleration? So if we've got an object that's got a velocity that is changing, so if it's got a changing velocity, it means it's got an acceleration vector. So we have to ask ourselves now, what is the relationship between them? So you've got 5 options here. So the acceleration vector must be parallel to the velocity vector. The acceleration vector must always have a non-zero component which is parallel to the velocity. There is no relationship between the 2 directions. The acceleration vector must always have a non-zero component which is perpendicular to the direction of the velocity, or the acceleration vector must be perpendicular to the velocity vector. So this is what you've got. You've got an object which has a changing velocity, and so the question is, what is the relationship between the velocity vector and the acceleration vector? So have a stab at answering that. Wow, okay, so we have a wide distribution. Each one has got its favorites. Okay, so turn to your neighbor and convince them that you've got the right answer. Okay, so let's have another vote and see what people have got. Okay, so we're getting a peak towards C, so I'll say that's good enough, and then I'll explain so that C is indeed the correct answer, if I can get it to go there. There we go. So C is indeed the correct answer. There is no relationship between the velocity vector, between the direction of the velocity vector and the direction of the acceleration vector. So why is that the case? Well, supposing we've got some object here, or in fact, let's say it's you. You are moving along with some velocity, right? So you've got some velocity vector here. So if you are moving along at some velocity, right, what are the restrictions on the direction that you change? So, and you want to change your velocity, right? So you want to turn to the left, turn to the right, speed up, slow down, whatever, right? Are there any restrictions on the direction in which you change your velocity? Right? Any restrictions? Right? If you turn to the left, is the ghost of Newton going to pop up and say, no, don't turn left? Right? No, right? You can change your direction in any way you choose. There is nothing to stop you moving faster, slowing down, moving to the left, moving to the right. you can change your velocity in any way you like. Now, so what this means is you've got a delta V here, and it may be fixed in magnitude, right? You can't necessarily, if you're running along at your top speed, you can't immediately just stop instantaneously, right? You'll fall over if you try. So you can't, always choose the you're limited by the magnitude of your change in the velocity, but the direction of the change of velocity is entirely up to you. You can change it in any direction you like. And so this is the point that sometimes confuses people is, so if you change it like this, the resultant velocity vector here will be along this direction now. So if you're moving at a very, very large velocity, you might be constrained as to what your resultant velocity vector will be after you've changed. If you've had 1 second to change it, you might not be able to change it very much. But nevertheless, the direction in which you change it is entirely up to you. I mean, if you imagine this was a spacecraft zooming along, it can spin in any direction it likes and points its engines and fire in that direction to cause an acceleration or a change in velocity. There's no constraint. So the direction of the acceleration vector and the velocity vectors are completely independent. There's no relationship between them at all. And because of velocity, an acceleration is a change in velocity, so it doesn't matter what direction it's pointing in, you will change the velocity vector. Even if you don't change the magnitude, you'll change the direction of the velocity vector, and that's a change in velocity. So there's no relationship between the two. So, slightly different question, very subtle change. Supposing now we're asking again the relationship between the directions of the velocity and acceleration, but now for an object which has a changing speed, right? So not changing velocity now, we're changing the speed. And so the question is, we've got the same options again, A, B, C, or D, but now we've got a change in speed. So think about it and push the button. Seconds. Okay. So that's because I want to get to the demo. So I'll say that's enough. That's maybe a little bit on the low side, but so most of you, or at least more than half of you, got it right. If the thing will get there and show it, yeah. There. This thing seems to, it goes slow and then it goes fast, and you never know which it's doing. There we go. Okay, now I'll hide it fast. So the correct answer was B. The acceleration vector must always have a non-zero component which is parallel to the velocity. So why the difference between when we're talking about velocity versus acceleration? Well, here, when we were talking about velocity, the acceleration vector is a change in velocity. So it doesn't matter what direction it's pointing in, it's going to change the velocity. But there's a difference if you're wanting to change the speed, right? So if I imagine a velocity vector here, and I change it slightly to point along here, and this is, if that's the center, this is the edge of a circle, then the magnitude of the first velocity vector is equal to the magnitude of the second velocity vector, and there has been no change in the magnitude of the velocity, and so therefore no change in speed. The velocity has changed, right? I've got a delta V here, so I've changed the velocity, but the speed has not changed because the length of the velocity vector has stayed the same. All I've done is I've just rotated it, right? So no change in speed, just a rotation in the velocity vector, and so in that case I haven't made any difference to the speed. And this change in the velocity, if you work it out, is when the change in the velocity is perpendicular to the original velocity direction. So if I'm always changing the velocity perpendicular to the direction of the velocity, then all I'm going to do is I'm just going to rotate this vector round, and I'm never going to lengthen it or shorten it. So in order to lengthen it or shorten it, I've got to have a component of the change that's in the direction of the original vector. right? So if this is my delta V, then I can split this into components, right? And clearly, if this component here is not equal to 0, then that implies that the magnitude of the velocity vector has changed. Right? So non-zero component in the parallel direction to the velocity means that I've changed the magnitude of the velocity. And since all I care about when I'm talking about speed is the magnitude of the velocity, that means that I've changed the speed of the object. And so the answer here was B. Acceleration vector must have a non-zero component parallel to the velocity to lengthen it or shorten it. Could be a negative component, doesn't matter. Okay, everybody happy with that? Right, so that's and then another subtle effect between velocity versus speed. Okay, so hints for dealing with the problems when you're dealing with 2 dimensions. Probably rarely will it be 3. It'll almost always just be 2 dimensions. Split it up into x, y, and z, or x and y if it's 2. And then use time as a common variable to all components. So when you're talking about a projectile motion, right, the amount of time from it leaving your hand to hitting the target or whatever it's going to hit, it doesn't matter whether you're considering with the x direction or the y direction, the amount of time it takes to hit the target is exactly the same. It's a common variable to both components, and so you don't have to, you can calculate it in one direction and use it to solve the equations in the second direction. And then just as with 1D problems, always be aware whether the acceleration is constant or not. Every time you see an equation which looks like an acceleration problem, you now need to be asking yourselves, is the acceleration constant? Does it change? Can I split it up into 2 regions of constant acceleration? Do I have to use calculus, right? Now at your university and we get to the calculus level, you have to be asking yourself that. It's not going to be like it was at high school where you only ever did constant acceleration problems because those were the only ones you could deal with. Now you have to start asking yourselves, is the acceleration constant? Because some questions, it's not going to be constant and you can't use those equations. And that's a common error that I see on exams is people use constant acceleration equations where the acceleration is not constant. So always be aware what equations you can use, which equations to use. Okay, so next thing we're going to deal with is projectile motion. So this is when we've got something that's freely falling under gravity. So it's got a constant vertical acceleration due to gravity, but instead of it just having vertical motion, you give it some horizontal motion as well, and so it follows the path of a projectile. So since gravity always acts vertically, there is not going to be any acceleration in the horizontal component of the motion, right? So we've got no acceleration horizontally, we've only got acceleration vertically. Well, so this makes things actually nice and simple. So, first thing we have to ask ourselves is what happens if we actually give something a horizontal motion, right? So we're going to have, and we're going to do this one here, so you'll know that I'm not, this is real experimental physics. So we're going to have 2 ball bearings. And one of the ball bearings, B, we're just going to drop vertically. So no, I'm not going to give it any horizontal component of motion at all. It's just going to drop vertically down. But the other one, we're going to hit it with a solenoid and give it a horizontal component of velocity as well. And so the question we want to know is, do we have to worry about the initial horizontal component of the motion when it comes to the vertical motion? So we've got a question, and this is, if we do this, which one of these 2 ball bearings will hit the ground first, assuming they're dropped from the same height? Will it be A? Will it be B? Will both hit at the same time? Or have I not given you enough information to be able to figure out which one will hit first? So we'll vote, and then we'll let the universe tell us what the answer is. So we'll stop there. Okay, so what have we got? Okay, so we have we have a prediction, so we'll see if the universe listens to democracy. So hopefully you can see that. So what I've got here is I've got a little solenoid, and what it's going to do is I've got a little tray here which will get yanked out from underneath the ball bearing, and the other ball bearing will be hit by the core of the solenoid, pinging in that direction when I turn on the electromagnet. So we're turned on. So we're ready? So you might not see it, but what you should do is listen, right? Because these things will make a noise when they hit. Right, so I hope that you heard only one whack when it hit, right? There we go, right. So, get it while it's working. So, indeed, the answer was C. Both of these hit at the same time. So, that's giving us our first indication that the horizontal motion that we give the ball doesn't affect the vertical motion, right? It doesn't matter that this has a horizontal component. So, one of the questions we can ask is what path does the ball trace? So again, I will go through this a little bit quickly, but you can follow the maths on the transparency. So what we're going to do is, since we've shown that we can split the two components up and treat x and y independently, we can write down the constant acceleration equation in the vertical direction, y, where we have the acceleration due to gravity, and we're saying down is positive. So downwards is the positive direction. And so we start with 0 initial velocity in the y direction, and so our y component is just a half gt squared. And then we can do exactly the same thing in the x direction, where our acceleration in the x direction is 0, but we do have some initial velocity. So this is v0x, the x component of the initial velocity, but no acceleration, so this term disappears, and we just end up with v0 constant, because this obviously is a constant, times time. So from this equation here, we can rearrange it and get that time is the x position divided by the initial x component of the velocity, and then we can substitute this value of time into this expression here for y, and what we end up with is that the y position is equal to g over 2 v0x squared. Well, this is just a constant. The gravitational field's constant. Initial velocity x component is constant, times x squared. So we've got y is proportional to x squared, and that path should be very familiar to you. It's a parabolic path. So we've just shown here that when you have projectile motion under a constant gravitational field, you will always end up with a parabolic path. The shape of the parabola will depend on how strong the gravitational field is and the initial component of the velocity in the x direction, but it will always be a parabolic path, right? So you're always going to end up with a parabola. Okay, so supposing we change things slightly differently, and we can again test this with the universe. So now what I've got is I'm going to start with a trolley, and in that trolley there's going to be a ball that's on the top of a spring. And what's going to happen is the trolley will pass underneath a tunnel, and just as it enters the tunnel, right, the spring will fire and it will launch the ball bearing vertically upwards. And so the question we're going to ask is, where will this ball bearing land? So this trolley's moving, constant velocity, just as it goes under the tunnel, pings this ball bearing up vertically. So does the ball land at point A, so back where it was launched, or does it land over here at the other side of the tunnel, either in the trolley here at B, ahead of the trolley at C, or behind the trolley at point D, right? So those are your options. It either lands back here where it was launched, or it lands in or in front or behind the trolley. So, and again, you don't have to take my word for it, we'll test it. So this, of course, is also an example of a non-constant acceleration, right? Because we're gonna give it a big impulse at the start. So, okay, okay, well you've all voted. I was going to give you 45 seconds, but I'm not sure you need it. 45, we'll stop now. Okay, so let's see what we got. Whoa, bit of disagreement now. So we've got A and D seem to be, you've got 20, well, almost 20% between you, and B though is still the overwhelming choice. Okay, well, let's see what happens. This is where this one actually has a slight chance of going wrong. Okay, so here's the trolley. This thing will hit the edge of the tunnel and launch the ball bearing, and we'll see if this thing works. So what we can learn from that is that this ball starts with an initial horizontal component of velocity, and the fact that we're hitting it and giving it a vertical acceleration for a small period here does not affect the horizontal component. It maintains the horizontal component of the velocity, and so while it starts a vertical motion here, right, so vertically it's going to go up and it's going to land back down again, the horizontal velocity it starts with is exactly the same as the horizontal velocity of the cart, and so by the time it's gone up and come down, the cart and it have moved directly above one another and landed at the same place. And in fact, there's a video, and if you look at it on a video, you can actually see that these two things remain directly above one another at all times. You can't actually see the cart when it's going through the tunnel, but you can see that the ball and the cart always remain in a line, vertically aligned like that, and it's just the ball goes up and comes back down again. So again, the two components are independent. We can solve them independently. There's no relationship between them. It's just obviously the time it takes for the ball bearing to go up and come down is the same as the time it takes for the ball bearing to go from here to here, right? Its time is the same in both directions. Okay, so what about calculating the maximum range for a projectile? And again, I'll go through this pretty quickly. There's there's a more difficult example that's worked through on the website where instead of a nice flat plane like this, it's an inclined plane, and you've got a Roman centurion firing rocks with a mangonel down a hill. And that's what's called a projectile on an inclined plane that's more challenging. But I'll show you the basic principle here with a nice flat plane to keep it simple. So what we've got is we've got some object here that's been thrown with a speed v at some angle theta above the horizontal. And the question we want to ask ourselves is, if we've got a gravitational field g here, what is the maximum range that we can shoot this projectile? And then if we've got the maximum range, we can also use it to calculate the maximum height. So what is the furthest you can throw something if you're throwing it at speed v, and what angle should you throw it at to get that maximum range? So what we're going to do, again, I'm going to go through this quickly, but I suggest that you go and look through it yourselves. So we split it into two components. And here we've got two nice simple components. We've got horizontal and we've got vertical. And so vertically, we can write down a constant acceleration equation, we ask ourselves, though, first of all, what do we know? Well, we know the initial y component of the velocity, that's v sine theta. We know the initial y component of acceleration, that's minus gravity, because we're taking upwards as positive. So always helps to make sure you know which way is positive. We have initial y displacement as 0, and time we don't know, but that's what we want to find out, because we're going to use that to calculate how far we go, and we're going to use that to calculate how far we go. So if we look at these quantities here, we don't care about the final velocity. So if we look at these quantities here, we want to use this constant acceleration equation. And then we just stick these numbers into this equation and do a bit of algebra. And the result that we get out of this is that the time is 2v sine theta. Remember, theta was the angle we launched the object at, divided by the acceleration due to gravity g. Now, in the horizontal direction, we have exactly the same quantities. We know the initial component of the velocity, that's v cosine theta. Remember, closing the angle, so it's cosine theta. We have the x component of acceleration is 0, no acceleration in the horizontal direction. Our displacement in x, if we go back to the diagram, we said that the range is a distance d here. So that's our displacement in x. We start here, we end up here. So all we care about is the horizontal component of displacement, right? When we were doing it in y, our vertical displacement was 0 because we start on the ground and we end on the ground, right? So vertically, 0 displacement, horizontally, displacement d. Right? So we put our numbers in here. This term goes away because we've got no acceleration. So we just get that d, the range, is vt cosine theta. And then we can use this expression for time that we got from this equation here, and we can put it in here. And if we work through the algebra, we end up with this expression here, that we've got v squared over g times 2 sine theta cosine theta. Well, at this point, we have to remember our trig relationships, which I'm sure you remember from love from school. 2 sine theta cos theta is just the sine of 2 theta. So we can replace this expression with sine of 2 theta. So now we've reduced our range here. We have an expression from the range of v squared over g times sine of 2 theta. So what we want to know is, well, what's the maximum value for the range? When do we have the maximum range? Well, sine here has got a maximum value of 1, right? Sine goes between -1 and +1. So our maximum value of the range is when this quantity here is equal to 1. And so that gives us a maximum range is v squared over g. So that's the maximum distance that we can throw the ball. Of course, we're ignoring air resistance here, but that's the furthest we can throw a ball. So the next question is, well, okay, when do we get the maximum range? Well, we get it when sine of 2 theta is equal to 1. Well, the sine, the angle that gives us a sine of 1 is pi over 2 radians, or 90 degrees. So that means that 2 theta must equal, I'll do it in degrees, here 90 degrees. And of course, that means that theta is equal to 45 degrees. And so therefore, we get our maximum range when we throw the ball at an angle of 45 degrees. And the maximum range we get is v squared over g. So this is just what we calculated here. And then if we want to calculate the height, all we do is we go back to the vertical component of acceleration. We use a slightly different constant acceleration equation, stick in our values for theta that we just calculated, and we can calculate the height. And the maximum height is v squared over 4g. So it's a quarter the maximum range is the height of the projectile. Okay, so we'll stop there, and we'll do circular motion and finish off kinematics on Friday.